Hi, good morning. I hope I'm audible at the back as well. So firstly, thank you, Roshni, for the kind introduction, and thank you for the organizers for this opportunity to come and present some of our work and discuss these topics at this platform. So today I'll talk about how to use reinforcement learning with the goal of making them work with real-world autonomous systems. So a lot of my research work is motivated by the increasing advent of autonomous agents in daily life. So what do I mean by that? So for example, you would have come across examples like these where robots are now being used to perform surgeries. So earlier when doctors would actually be over the body, now doctors are at a console somewhere else and they're teleoperating a robot to do the surgery. Other examples include maybe disaster response, where you have a team of operators operating mobile robots or drones to perform rescue missions. Further examples include, let's say, sorry about that. Other examples include surveillance and inspection of key assets like, let's say, oil pipelines, gas pipelines, electrical power stations, etc. And finally, something that's much more closer to my heart and something I've worked on myself is self-driving vehicles, autonomous vehicles. So for example, Waymo has been rolling out autonomous vehicles in select areas with some limited success so far, I would say. And that's an example we'll keep coming back to throughout this session. So let's look at two videos to sort of set the stage. On the left, I'm showing you a video from the DARPA Urban Challenge, where they were trying to drive autonomous vehicles through a prescribed track. And as the video here shows, we have two vehicles. We have the MIT and the Cornell vehicle, and at some point they both collide here. And the key issue here is that they don't know what the other agent is going to do. And this might seem like a toy example to you right now, but it's also very relevant because if you think about Waymo vehicles right now on highways, so as the second video is going to show, here is a vehicle that I'm sort of tracking. And after a while, we see a Waymo vehicle on the side there with the goal of trying to merge into this busy highway. Now, as humans, we tend to do this task very easily, right? All of us drive and we merge into busy highways all the time, especially in Kathmandu roads. As I've been saying, it's really hard to drive. But as you can see here, the Waymo vehicle is still waiting, even after all this time. And it's waiting for an opportunity to come into the busy highway. Now, the question here is, how can we make autonomous agents like these learn to be safe? So, can safe autonomous behavior be learned? Now, why have I bolded the word learned here? The point here is that, as you would say, that autonomous vehicles are already on the road, they are working, but they require tremendous amounts of human input and domain knowledge. They require plenty of person hours of coding and trying to, come up with all these corner cases and trying to defend against what might happen in various situations. So the premise here is that can we use techniques from machine learning, specifically reinforcement learning, to completely learn this automatically without requiring much human knowledge or domain programming. Okay. So what you might say is, how do we try and attack this problem, right? If you go back to the previous slide, the key issue here was how do we model human driving behavior. So as humans, when we drive, we also try and model what you might be doing. So if I'm driving, I might look at you and think, oh, you're a very aggressive person. You might come and crash into me. So internally, I'm kind of modeling your behavior in a certain way. And like the previous session discussed, there is an underlying sequential decision-making problem here. So at every time step, what would the driver do, okay? So what you might say is, hey Raunak, let's just do supervised learning, right? So let me go and record data. So let me maybe fly a drone or mount a camera at the top and record data of humans driving on these highways, okay? And then my goal becomes, can I learn a mapping between a situation on the road, so a state, and a steering or an acceleration command, the action, okay? So what happens if we try this? So we tried this and what happens, let's see. So on the right, you'll see a video where the blue colored vehicles are all driven by the policies learned using this supervised learning approach. And the green vehicles are just, let's say, recorded vehicles driving along. Okay, so here is what happens. So whenever you see red, that means collisions happening. Whenever you see yellow, that means the vehicle's off the road. So as you can see here, things are not looking very good at all, right? The vehicles start crashing. There is a huge problem here. Vehicles are going off the road, and so on and so forth. So take a moment to think about why this might be the case, right? Why did supervised learning directly not just work in this problem? Okay, so to contrast these two a bit more, let's say a bit more from a technical standpoint. On the left, we have our traditional cat-dog classifier image. On the right is what we have seen in the past session, is a reinforcement learning loop, where the worldview is that of an agent which interacts with the environment and gets a reward and a new state back in this continual loop. Now, on the left, what happened? What is the input and the output? Let's think about that. So the input is, let's say, some feature vector x. The output is some label y. The data set given to you is a set of tuples x sub I, y sub I. And the goal is to try and learn a function, let's say parameterized by theta. So f sub theta xi should be approximately equal to y sub I. Clear? So familiar to all of you. On the RL side though, there is a bit of a difference. What is the difference? So the input now is a state s sub t at each time step, right? So st, and the output is what action should I take at each corresponding time step, a sub t. And the data is the key point here, right? On the left, someone gave you the labels. Someone said, at x sub I, take y sub I. On the right, the data is basically trajectories. So the agent goes and tries things out in the world and gets a sequence S1, A1, R1 through ST, AT, RT. Okay? And the goal now is to learn a policy, let's call it pi sub theta, which is a mapping from state to action. Now in this context, I'm presenting it as a deterministic policy. It could also be stochastic. So it could be mapping from a state to a distribution over actions. Okay? And the goal, and we'll formalize this subsequently, but the goal notionally is to maximize total reward obtained. Now what does that mean? We'll talk about this subsequently in a more mathematical sense. Okay? So just to contrast, in the left, someone gives you the true labels. Okay? This is known during training. And there is a very key assumption that we make. It's IID. So what does that mean? It means that all the samples that you get are independently identically distributed. So they are drawn from the same distribution and independently. Now think about why this might not be the case in the RL setting. So why might IID not be true in the RL setting? So in the RL setting, what we have is there is no ground truth. No one gives you the labels. And there is no notion of, let's say, right or wrong. All we have is a reward. And like we saw in the previous session as well, the reward could be quite misleading. And we'll talk about this a bit as well. And the second and more crucial point is there is no longer the IID assumption holding. Why might that be the case? Because the previous outputs will influence the future inputs you get. So think about the driving problem again. If I'm trying to learn from some driver, what they did at time step t minus 1 influences what I'm going to see at time step t. And this breaks the IID assumption. Okay? All right. So just to now sort of contextualize a bit more. So supervised learning and reinforcement learning have different causes for excitement. Okay? So on the left, what we are seeing is what might be impressive for us in supervised learning, right? So this is impressive. Why? Because it looks like something that a person may have drawn, right? So we are impressed because these pictures might have been drawn by humans, and the amazing thing here is that a machine, an agent, is able to do these things, draw these pictures. On the right though, what we are seeing is a couple of pundits discussing the AlphaGo, the famous AlphaGo game. And what they're talking about here is a certain move called move 37. Now why is that famous? Because it's a move that no human could have ever thought of. So the excitement factor here is different. But the excitement factor here is we are happy because on this side, it's something that is better than what a human may have done. So now if you think about it from a broader perspective, on the left, we are doing things that humans are already quite good at, right? We can do good visual perception, we can do good language communication, and agents are able to do that right now. So we are very happy. On the right is something humans are not very good at. So if you think about things like decision making, policies, let's say climate change, right? Humans are very myopic often. And the key point here is that can agents help humans become better at making sequential decisions? That is the whole premise behind this area. Okay, so with that setup, I'll just quickly walk us through what the outline of this talk is going to be. So we'll first think about RL in terms of how to contextualize it in the broader AI landscape. We'll look at some example MDPs. I know you've done this in the previous session in more detail, so I'll just quickly walk through those. We'll talk about what policies mean and what objective function we are trying to optimize in this context. Having done that, we'll next go into discussing more about policy search. So in the previous session, we spoke about value function based methods. But in the autonomous system setting, the important thing is to be able to search over the space of policies. So we'll talk about that. So here we'll cover ideas from optimization such as random search and policy iteration. We'll then talk about deep RL for policies. So how do we take the ideas developed in the previous part, so policy iteration, etc., and translate them into the deep RL setting, so where approximations enter the picture. And then we'll talk about how some recent extensions have been built around these foundations, namely inverse reinforcement learning or imitation learning. And finally, we'll talk about some recent research direction that we are pursuing in our group. Okay, so let's begin the contextualization. So here is a spectrum of AI methods. So on the extreme left, we have retrieval-based methods. On the right, we have reasoning-based methods. So think about where you might place different methods here. So for example, where might machine learning be placed, right? So on the extreme left, we have reflex-based methods. So here you have things like regression, nearest neighbor. So machine learning is a reflex-based method. Why? Because once trained, the model just outputs the resulting y sub I, okay? There is no more reasoning going on. On the other end of the spectrum, reasoning, we have logic-based methods. So for example, we might have temporal logic, we might have model checking, and then there are things in the middle, right? So we might have variable-based methods. So you may have heard of things like CSPs, right? Constraint satisfaction problems. Or you may have heard of Bayesian networks. And then we have state-based methods, which is where RL lies. So here what we talk about is, let's say, search problems or Markov decision processes. So just to contextualize again, what we are doing is we are living in this vertical of this entire spectrum of retrieval from reasoning, okay? Okay, so now let's look at an example MDP. So you already know what an MDP is. Let's think about a specific example called the queuing problem. So imagine that you're running this hot dog store or a burger store or whatever, and you have to serve customers as they come, okay? There is only one queue. The line is initially empty, there is only one queue, and there are two modes of service. So let's say you're managing this store, and you can have your workers do either a fast service or a slow service, okay? And there is a horizon T, so this queue will last for T time steps. I mean, not the queue, the whole process will last for T time steps. And the waiting cost, I mean, the customers get unhappy if they have to wait too long, right? So there's some gamma times the queue length. So why might this be a relevant problem? Think about things like job server scheduling, right? So if you have different jobs coming in, how do you assess which job to assess to which GPU? Do you give the L40S or do you give the A100 or the H200, right? So it costs more to give you a faster service, but you have to also make the customers happy. So think about how you might try and formulate this problem, right? So what you might do is you might start with some state space. So you have, is this visible at the back? Yeah, okay, great. So you might have a state space which is length of the queue, right? It can take values 0, 1, 2 through whatever, right? And the line initially starts from x not equal to 0, okay? And then you have two modes of service. Let's call them fast and slow, FS, and the completion probabilities. So QF is more than QS. What does this mean? It means that in one time step, what is the probability of completing my job? So naturally, if you're doing a fast service, you will complete faster, right? Hope this makes sense. Okay. And then you might have a cost. So now, as we spoke already, you might have to pay more cost if you're doing a faster service. So Cx sub t u sub t is gamma xt plus dut. So this gamma xt is, as I spoke, the waiting cost, so how unhappy the customers get. And this dut is a service cost. So as you might expect, you will pay more if you have to do a faster service. So df is more than ds. So now this is basically state space and the action space. So action space is what here? It's the service mode, fast or slow. So now how would the system transition? So let's think about that. You need a transition function for this MDP. right? So there are two cases. If the line is empty and if the line already has some customers. So think about what the transition functions might be, right? So if the line is empty, if x equal to 0, so this top case here, what you might have is the probability of x becoming 1. What is that? So it's the probability that the new customer arrives, right? So it's the probability p, okay? And then you might have probability that line stays empty itself. So p x prime equal to 0, given x 0, u is f or s. This is 1 minus p because it's probability that no new customer has arrived, okay? On the other side, if the line is already not empty, then what are the three cases? There are three cases now. Case 1 is that the line grows by a length of 1, so a new customer does arrive. So the probability is p times 1 minus q of u. Why is that? Because a new customer arrived and the older customer was also served. So the line grew by length 1. Or the line might stay at the same length, so x prime, px prime equal to x, or the line might reduce by length 1, okay? So reduce by length 1 when a new customer has not come and the existing customer has been served, okay? So hope you're with me so far. So that's basically an example MDP as to how you might try and formulate this queuing problem. So just to repeat, what we did is we first said what the states and actions are. We then said what are the transition probabilities, and we stopped there. We didn't solve it, okay? So one thing that to establish now is what is a policy, right? So you may have, sorry, you may have seen AI courses and you may have seen pictures like these. So this picture is showing us basically a path planning problem. So you have a starting state S and a goal state G, and there is a graph given to you as such. And then your task becomes, how do I find a path, let's say a shortest path from state S to state G. Now the key point here is what you output. The output you get from this is basically a plan. A plan means I will start at S, go to A, go to D, C, E and F, okay? Now why is this not enough for our needs? Let's think about that. So the key point here is that in this problem, if you take an action A from a state S, the transition to the next successor state is deterministic. So if I go right from state S, I'll end up at A 100% of the time. There is no uncertainty here at all, okay? So it's something like, the example I like to give here is that if I want to exit this room from the dais to the door, I take a look and I make a plan. I'm going to go here, 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 here and there, right? Then I close my eyes and I walk. Now suppose someone at that row puts their leg out and trips me up. I can't help it, right? I can't do anything. So my planning has to be aware of that chance of uncertainty, okay? So therefore, what we need to think about now is a different case. So let's think about this example here. So you can start at S0 and then you can either go up or down at each state. So there are two actions, it's a binary tree. You can go either up or down, and just at the first state S sub 0, if you go up, you end up at S1 or S2 with probability 0.5. Okay, so that's the problem, and the question to you is, what is the value of taking various plans here? So suppose I would say I'm going to go down and down at both. My plan is down, down. What would I end up at? What do you guys think? Where would I end up if I do down, down from S0? Here, right? S8. So if I do down, down, I'll get 20. If I do down, up, I'll get 20. What if I do up, down and up, up? What happens then? So what is the value you might get? Can you just think about it? Yeah, so what you might get is, you'll get, if you do up, up, you get 15, you get up, down, you get 15, right? So even though you can see 30s here, the logical thing, rational thing to do is always go down at the first step, right? So here is where a policy matters. A plan will not cut it anymore, because a plan will say, why don't you just go up? But if you go up at the first time step, you might end up at the 0 node as well. So what is a policy? A policy basically says, I'm going to look at each state, I'm going to look at the state, and then map an action from that state. So just to bring it back to my example, if I now have to go outside the room, I open my eyes, I keep my eyes open, I go there and I check, are you going to trip me up? I keep checking, and I go. That's my policy now. Okay. So this sort of differentiates policy from plan. Okay. So now having established that, what is the RL objective? So the objective is as follows. Suppose we have a policy pi sub theta A given S. So it's a distribution over actions given a certain state. The state is S here, and the policy could be a deep net, could be a decision tree, whatever fancy thing you want. And once you query the policy at the state S, you get an action out. So you get an action, and then you pass the action to the world. So that is the environment, as was discussed earlier. And the environment is doing what? It's just doing a transition function. So there is a PS prime given SA that governs the environment, and the environment responds by making our system go to a new state S prime. Okay. And just one clarification point to make here is this A could be sampled from a distribution as well. So if the policy is stochastic, I'll sample A from a distribution. So what this process does is it induces something called a MDP, what we have seen already. MDP looks like this. So you start at a state S1. So S sub 1 means the state of the time step 1. You take an action here, A1, and the SA combination induces the next state S2 and a reward R1. And you keep evolving this MDP forward and keep track of what the rewards you get are at each time step. So in the queuing problem, for example, you will basically say, okay, I did a fast service and I got this reward. I did a slow service, I got this reward. Keep track of it. And in expectation, over the time horizon, I want to maximize my cumulative sum of rewards. Right? So how will you see that mathematically? What you'll say is theta star, so the parameter of the policy, the optimal parameter value theta star is an argmax. Argmax over what? Expected value of sum of rewards over the time index t. Okay? And the expectation is over what? It's over something called tau. So tau is basically trajectories. So if I go back to the previous slide, you get these sequences, right? We call them trajectories, and you sort of keep a log of them, and you take a average essentially over these set of trajectories. Okay? So that is the RL objective. So hopefully you're with me so far. Any questions at this point? Okay, great. So now the next question is, we are harping about policies so much. So why do we care about policies so much, especially in autonomous system setting? So here is an example that will make it clear, hopefully. So this is the Atari breakout game, which you all may be familiar with, one of the RL success stories. So here the idea is, can you move this paddle to be able to break out of this wall and then get reward? So the reward is very evident. It's basically a score you get at the top here. Now, as you see, this agent is not very good at this point. It's being trained. So it's kind of getting some score, but it's also moving and losing the ball plenty of times. And this is actually a DQN based agent. So DQN means what? There is someone who's sat down and thought about the value function in this problem, done a search over value function space and found the optimal policy. And eventually, at some point, the agent becomes very intelligent and finds a strategy. So it basically says, I can tunnel through a certain point here, through this region here, and then the ball automatically gets plenty of score by itself. Right? However, the issue here is that I have to still reason about value functions, which is quite tough in this problem. My goal is to try and control this paddle, right? The paddle can do only two things, go left or go right. So why reason about value functions at all when we can just search in the policy space? So that's the point here, that in autonomous systems especially, right, we can do a search in the policy space. And why? Because firstly, as in this example, it's easy to specify. So I can just say, hey, take the paddle, go left or go right. That's it. No need to think about V's or Q's. The second point is that the V, if you do value function based reasoning, it needs a one-step look ahead, meaning you need to know what the model is. So you need to know what the transition function is, for example. In the queuing problem, we said this P x prime given xa. If we can find that, only then can we use value V based methods. And then in the previous session, you also saw something called Q, right? Q based methods. But the issue with Q is it does not work in continuous action spaces very easily. Why? Because it needs an argmax over the actions. So these reasons motivate the thing about policies and searching over policy spaces. So what we get is, based on this discussion, we get a layout of what RL algorithms exist. So here is a picture. It's basically got two sides. On the left, we have policy optimization. On the right, we have dynamic programming. So value function based methods live here in the DP world, okay? And the policy optimization based methods, they include things like derivative free optimization or evolution, policy gradients, actor critic methods, which we'll cover in this talk, okay? So just to summarize at this point, what we've seen is that there are basically a lot of methods in RL which belong to two categories broadly, the DP and the PO category. And in this talk, we'll focus on the policy search side of the story. So how do we directly search in policy space? So let's think about maybe a first recipe, right? What is the first thing we can do? And this will talk about DFO. So this DFO stands for derivative free optimization. So it's basically zero order methods. So a recipe could be as follows. The objective is this, right? We spoke about this already. And what we can do is just change the parameters randomly, right? Just try something out. If the result improves, keep the change. And if the result does not improve, throw away the change and just repeat this process. Okay? So if you has anyone here heard of hill climbing? Yeah? Okay. So hill climbing is something that is kind of in this family. Okay. So let's talk about zero order policy search methods in the next section. Okay? So before doing this, I want to just introduce an example problem that will help us sort of contextualize this further. So this is called the regulator problem. Okay, what is this problem? So what we have is we have a state action space that is single valued scalars, right? So S and A are both scalars that can take real numbers, so belong in the real number space. And the initial state distribution is given as follows. The S naught is sampled from a normal distribution with mean 0.3 and variance 0.01. Okay. Now there are two things remaining. We have to specify what the state transition is and what the reward function is in this problem. So the transition function is as follows, that S prime is sampled from a normal distribution again, and the normal is basically S plus A and with variance 0.01. So what does this mean? That if I take an action A at a state S, I will draw a Gaussian around that state S, state S plus A, and then sample from that Gaussian. And then what is the reward function? The reward function is RSA is negative S squared. So think about what this reward function is doing, right? What does this do to the system? It says that anytime you're not at 0, I'm going to penalize you. So it's a quadratic function which is negative, right? So this will naturally drive the system to try and go towards the origin. Okay? So think about why might this be a relevant problem? So which problems might have this kind of structure? So any thoughts? Pole balancing, exactly, right? Absolutely. You can also have HVAC systems, temperature control, regulating temperature, where LQR is used often, right? So think about those systems. So absolutely. So the relevance of this is the pole balancing problem, and so what it looks like is this. So you have a cart pole, and you're trying to make this pole stay upright, and all you can do is control the cart's velocity towards right or left. And this is showing an actor critic based method, which eventually ends up making the pole stay upright. Of course, there is a trick here. The trick is that you have to first bring the pole into the region where your dynamics obey nice linear properties. Okay, so you first get it close to the upright position and then do actor critic, so policy gradient based methods to try and make it stay upright. So at this point, it's almost there. It's able to make it stay upright for a while. Okay. And fundamentally, this problem can be modeled as a regulator problem. You're trying to keep the pole upright at this center point. Okay. Okay. So it's known from control theory that the form the optimal policy takes in this problem is basically A star S is negative KS. So you apply a negative gain to the state, and that is the action you have to take at every state. Okay. So in this case, we want to try and translate this to policy search. So how might you parameterize the policy in this context? Let's think about that for a moment. What you might think about is something like this, that the action is sampled from a Gaussian with two parameters, theta sub 1 and theta sub 2. Theta 1 tells us what the mean value is, so theta 1 S, and theta 2 tells us what the variance should be. Okay. So hopefully all clear so far. Basically what we know, this is a toy problem. Why? Because the solution is known to us already. Solution says just do negative ks. But I'm trying to say how can we do policy search to try and find the solution negative ks. So hopefully what you know is at this point what we'll try and do is we'll try and find theta 1 which is negative k and theta 2 which is close to 0, right? This will match our expected solution A star S. Okay. So at this point, let's maybe just look at an example to formalize this a bit further. I'll change to a notebook. Hopefully it shows up. Okay, yeah. So this is the regulator problem. I just coded it up in NumPy. So what we have is we have some imports in the beginning. Is this visible at the back? No? Okay. Need to zoom in a bit more. How about now? Better? Okay. So this function state transition is basically telling us how is the system evolving. So you take S comma A and some sigma value and you return a random normal, right? S plus A comma sigma. And then the test policy, what we are trying to test out is negative k times S. So what we'll do is we'll take this system. System is given to us as follows. The sigma is 0.1. The initial state mean is 0.3. So we saw this on the slides already, and I'm just repeating it here for your benefit. The initial state standard distribution is 0.1, and we are trying to simulate the system for 100 time steps. Okay, and we'll just try different values of k. We'll try 1.99, 2.01, 2, and 1, and see how the system behaves. Okay. Okay. So we saw this. Okay. So now we'll talk about few methods that can do random search in the policy parameter space. Okay. So these are derivative-free methods. We'll talk about derivative-based methods in the next part of this lecture. So the first thing I will talk about is something called the Hooke-Jeeves method. It's a local search method. Anyone seen this before? Hooke-Jeeves methods? Okay, cool. So some of you have already seen this. So hopefully it's a useful review for you. So what you have here is, this is a test function we are talking about right now. This test function basically has contours that look like this, and the lighter colors show the value of the function reducing. And our goal is to try and minimize this function. So we are trying to go close to the center point of this function. So I'll first show you some visuals of what the Hooke-Jeeves method does, and then we'll try and characterize this algorithmically. Okay. So what we do is we start with some initial point and we search in the 4 coordinate directions. We just take a step alpha in all the 4 directions and we evaluate the function at each point in these 4 directions. And then we say, okay, for which point here am I doing the best, right? So think about which is the point you think you'll do the best out of these 4. How many votes for the bottom one? Anyone? Cool, okay. So all of you think of the top point, right? You should basically be moving up. Why? Because it's taking you close to the optimal point that you want to get to. Okay? So you take a step to this point, and you have now moved here. You again do the same process, right? Search in the 4 directions with a step size of alpha. And next you'll move where? Where do you think you'll move? Either this or this, right? The right one. So you have moved here at this point, again do the same thing. And now it becomes a bit tricky, right? If you go anywhere, you're trying to go away from the optimal point. So what do you do now? Stop? Yeah, you could stop, but there's one small thing to check. The check is that if I try a smaller step size, I might find a better point, right? So here what I've done is I've taken the method takes a smaller step size, half the step size, and finds maybe a better point. And then at some point what happens is if you go in all the 4 directions, in none of them will you make an improvement at all. So then you stop. Okay? So again, just to summarize, we saw a test function. This doesn't have anything to do with the problem we are thinking about right now. We'll come to it later. This is a test function. We're trying to see what Hooke-Jeeves method does on this test function. So the recipe is as follows. We initially guess some x naught. We explore in all the 4 coordinate directions. And we move to the location that gives the best improvement out of all the coordinate directions. And if there is no improvement, we make the step size smaller and repeat the whole process. And at some point we find that no matter what we do, we can't improve, then we stop the whole process there. Okay? This was the Hooke-Jeeves method on the test function problem. So now let's see how it does on the regulator problem, which we actually care about ourselves, right? So here is a contour plot of the regulator problem. So on the x-axis, what we have is theta sub 1, which is the first parameter, and the y has theta sub 2, the second parameter. So we start here. Let's say we start with this initial guess of the parameter space, and we move left to right and then up to down. So eventually what we find is that this method takes us to a point which is close to -1 on theta 1 and almost 0 on theta 2. So this shows that the method has indeed worked on this regulator problem and has taken us to -1, 0, which is where we want to go. Okay? Okay, so hope this makes sense. So this was one method. The second method I'm going to talk about is cross entropy method. Anyone seen that? Cross entropy method, CEM? Okay, some of you. Okay, cool. So how does this work? What it does is, suppose my goal is to try and optimize this function in the dark black line here. Okay? So I'm trying to find basically this point essentially. So what I do is, this is a sampling based method. I basically sample on my design space over here, and I basically select a bunch of points here, and then I rank between those points in a certain way. How do I rank them? So in this plot you're seeing crosses and zeros. The zeros are the elate samples. Okay? So I've taken this underlying function, which I don't know what it is, and I've drawn these samples from it, and I find that, okay, out of these, all the circles are doing better, right? They're higher valued design points. So then what I do is I take these points and then I fit a Gaussian to it. Okay? So here in the first point, the gray line shows my fit Gaussian. In the second point, in the second picture, I'm seeing that the Gaussian has become a bit closer to all these elite samples. Then the process repeats again. So I draw more samples from this Gaussian, and I get maybe these kind of points, and I get these elite samples now. So now again my Gaussian becomes closer to this, and eventually my Gaussian has now almost converged on my optimal point. Okay? So just to repeat again, the idea here is that maintain a Gaussian distribution over the design space. So in our case, it would be maintain a Gaussian, bivariate Gaussian over the parameter space theta 1, theta 2, and sample points from it. So initially you're sampling from a very high entropy, very random looking Gaussian, and eventually you hope that the Gaussian becomes more and more converged to the optimal point. And this is called the cross entropy method. So how does it work in an algorithmic sense? What you do is you initialize some mean and variance parameters of the Gaussian, and then iterate. You sample n parameters from this Gaussian you created. For each of them, perform rollout to get return. So return is the reward that we spoke about, right? So you take these parameters, run the system forward, and see what kind of returns you got. Select the top performing ones, select the elite samples from these, and fit a new diagonal Gaussian to it. and then update your parameters mu and sigma. Okay, so that's how the whole method basically works to try and find the optimal parameters. So how does this method do on the test function first? So this is a test function again. It's called the Brannin function. It's got this kind of a contour space where you've got different optima, different minima, 4 of them actually for this setting. So your hope is with this kind of a CEM based search, you can at least find one of these optimal points. Okay. So how does this look? So here is the contour plot. You start with a very high entropy Gaussian distribution, bivariate Gaussian distribution, and you sample a bunch of points from them. And all the black ones here are the elite samples. Now why are these elite? Because these black ones actually close to the optimal point here. So they'll give a higher or a lower function value in this case. So then you take these black ones, and what is the next thing you do? You try and fit a new Gaussian to these black points. So what you get is a Gaussian that looks maybe like this. You sample from this again, you get a few more elite samples, black points here, and so on, and eventually you get a very tiny Gaussian that is converging near the optimal point. So this one has basically found, I think, this optimal point in the test function. Okay. So hopefully you guys are with me in this journey. Awesome. Okay, so now how does this look on the problem that we care about, regulator problem? So here's what it does. It basically starts with a Gaussian again, and eventually it converges to a setting which is close to -1, 0 via a bunch of different Gaussian that you're trying to fit. Okay. So this was basically 2 methods, Hooke-Jeeves and cross-entropy method, which used no derivative information. They were doing search in the parameter space directly without any gradients or derivatives. And we found how they can work in the parameter space to try and find the optimal values. Okay. So now you might say, okay, this is great. It might work well for certain times, but can we do something better, right? So what drawbacks do you think this method has? So maybe if you can think for a moment, what is bad about this philosophy, right? You just search randomly and try and pick better points. What is bad about this? Okay, so if there are multiple maximas, you might be in trouble, of course. I think the more important point is that you're throwing away information about the problem. So you're just doing random jumps and trying to see, okay, what works? I'm just trying to shoot in the dark and seeing what works, essentially, right? However, the caveat is that these methods work very well in some problems. So by no means can you write these methods off. For example, in the game of Tetris, which is a long-standing challenge in RL, the CEM methods actually are the state-of-the-art methods. They get the highest score. So it's an open question even now as to when do these methods work better and where do other methods work better. So my point here is that you should always keep these methods also in your mind and try them out for certain problems. Okay, so what we'll see next is something called policy iteration. So in the previous session, what we saw is methods based on value functions. But as we spoke, this session focuses on policy searching based methods more. So now we'll talk about policy iteration, and this will become a bit more technical at this point. Okay. So what is the problem, right? The problem is given an MDP M, which is characterized by the tuple S, A, P, R, and gamma. Just to remind you, S is the state space, A is the action space, P is the transition matrix, R is the reward function, and gamma is a discount factor, right? Just as a reminder. The goal is to find pi star, which is an optimal policy mapping from state to action. Okay. So what does this method do? What does policy iteration essentially do? So what we saw so far is a recipe that basically says, I am going to do random parameter searches and just select the better ones. But the issue was, can we do more intelligent things than that? And this is the first method that does that basically. So what it does 2 steps. That is, the first step is policy evaluation. So you give me some policy pi, I give you back what is the Q value for that policy. So how good is that policy essentially, right? So find Q pi t SA for all S comma A pairs. And just to make an important point here, in this setting we are still in the tabular state space setting, right? We are still in the grid world kind of setting, and we'll relax this subsequently. But right now, for the development of methods, we'll think about tabular settings. Okay, so think about grid worlds or discrete state action spaces. So the first step is policy evaluation, find Q pi t, and the second step is policy improvement. So take this q pi t and be greedy with respect to it. So take an argmax over A, q pi t s comma A for all s. So now why is this interesting? It's interesting because, as we mentioned, RL is a sequential problem. There's a bunch of time steps that have to happen, right? So if you're trying to, let's say, make a robot learn to walk, the robot has to walk for a certain distance and it has to take actions at every time step. The beauty here is that if you know q pi t, you can be greedy with respect to just that one time step. This q pi t captures for you the entire sequence of what might happen in the future. So you can just say, at this time step, I'm going to take q pi t s comma A and just be greedy, just be very myopic, and it still works. That's the beauty of this algorithm. Okay. So now we'll talk about basically these two things in a bit more detail, right? What do these steps actually entail? So just to summarize, there are two steps: policy evaluation and policy improvement, and together they're called policy iteration. Okay. So let's think about policy evaluation first. How does this actually work? So we'll take a grid world. So what does this grid world do? So here the grid world is set up as follows. What we have is, we have this 5 by 5 grid. There are two locations A, B and two locations A prime, B prime. The agent can basically take 4 actions in the cardinal directions, okay, north, east, south, west. And in state A and B, the agent is teleported to B prime and A prime no matter what it takes. So if the agent goes to state A, if it takes left, right or whatever, it has to go to A prime, no choice. Same for B. And for A prime, and if it does these transitions, it gets plus 10 here and plus 5 here for these transitions specifically. And if the agent goes off the grid, then the reward is -1. So it gets penalized for going off the grid. Okay. The discount is set to 0.9 in this problem. So now think about, if you think about a random policy completely called equiprobable policy. So what is its value? Let's think about that. So the goal here is, take this grid and give me a q s comma A for each point in this grid, basically. That's the problem I have here. So what you get is, if you do policy evaluation, what you get is something like this. So all the points here are basically V values for all these grid cells. So V of S. Let's think about this. Why does this make sense? So let's think about this row first, bottom row. So they're all negative values. Why do you think this makes sense? Yeah, so someone said that when you're here, if you take a random action, there's a very high chance you'll exit the grid. So you'll get a penalty of 1, basically. So let's think about these two values now, 8.8 here and 5.3 here. So why does this make sense? So if you go from A to A prime, you get plus 10, but the value is 8.8 here. If you go from B to B prime, you get plus 5, but the value you get is 5.3 here, it turns out. So why does this make sense? So what you might think is that if you take this transition A to A prime, there is a chance that from A prime you might exit the grid and get a negative reward, right? Therefore, what you have as the value V of S is less than 10 here, it's 8.8. On the other hand, if you look at B, if you take a transition to B prime, you get plus 5, but then you won't be exiting the grid, you're still safe. So you have a high chance of coming back to A or B and getting more and more rewards. So therefore the value V of S is more than 5 in this grid cell, it's 5.3. Okay. So just to recap, you have a grid world problem and you're trying to find the value, evaluate the random policy. And what you get is this kind of a value function here. Okay. So what's the theory here? The theory is that the policy evaluation problem is actually a fixed point problem. What does that mean? So I'm trying to find q pi t SA for all S comma A, and the claim is this is a fixed point problem. So why is that? Let's think about that. So as you saw in the previous session, the Bellman equation is this, that for all S, my V pi S has to satisfy this property. It has to be R S pi S plus gamma times expectation over the value over the next state, S prime. So you've seen this, right? So it turns out that this is actually a fixed point equation. So I hope you're seeing this. It's because in a vector form, what you have is V pi is capital R plus gamma P V pi. So think of V as a vector over all the states, Think of R as a vector over all the state action pairs. Think of P as a transition matrix and V as a vector again. So why is this a fixed point equation? Can anyone maybe intuit about this? So it's a fixed point equation because you're operating on V on both sides, right? You basically, so it's something like x star equal to fx star. That's a fixed point. So the question I wanted to think about now is, how do you find x star equal to fx star for a general function f? So any thoughts? Sorry? Iteration, right? Absolutely. So what you might do is, one recipe you might follow is initialize x naught in the domain AB. Let's say the function is defined on AB, and repeat xt plus 1 is f of xt. So just keep applying f to the function, to the design point xt at every point. Okay? Now the question to you is, when does this approach actually work? So let's take a step back. The context here is that the value function equation, Bellman equation, is a fixed point equation. To try and find a policy evaluate a policy, I have to try and solve this fixed point equation, right? So we are saying that this approach actually finds fixed points. It's a proposal that we have put. Now when does this actually work? Sorry? Convex function, okay. Is that the only case that it works? Convex, yes, but is there something more general? So the idea is that if f is a contraction mapping, then this approach will work. What does that mean? So it basically means that if you apply f, right, you take 2 points x and x prime, you apply f to both of them, then the distance between fx and fx prime will not blow up, basically. That's the whole point, right? So in more technical terms, for all x prime pairs, the mod of fx minus fx prime is less than or equal to gamma times x minus x prime for some gamma belonging to 0, 1, 1 open. Okay? So think about this visually, right? You have a function f and you have multiple points. You're applying this f to these points and you're trying to see how far away am I getting. And it turns out that these points are going to slowly come close to each other, right? And then the point is that if you do this approach, then xt will tend to x star as t tends to infinity. So now the whole game is very clear to us. We take this approach and throw it onto the value function problem, right? You give me a policy pi and I ask you what is the value of that. You're going to say, let's do a fixed point approach to try and find the value of that policy. Okay, so policy evaluation, how does it work? So the algorithm is called iterative policy evaluation. So just one point here before that. If you think about this, right, think about this equation. Can you think about a linear algebra way of solving this? Right, you can move v to the left side and then it becomes basically you have to invert a matrix and compute the value function. The issue there is it's an order n cubed computation. So it becomes very expensive very fast. So if the state space is of dimension n, then this becomes an order n cubed computation. Okay. So what we have is an alternative called iterative policy evaluation, which is a fixed point finding approach basically. That's computationally faster, could be faster, not always. Okay. So the idea here is that you start with some initialization v0. So you start with some random guess on the value function. So make a grid, fill all the squares with some random value, whatever you want, between 0 to 1 by 1 minus gamma. That's a technical requirement that we are not going to discuss too much here. And repeat the following process. Just take your v and apply the Bellman equation to it. That's it. Okay. If I go back to the grid picture, you'll start with some random values here and just keep applying the Bellman equation repeatedly to that grid. And eventually what you'll do is you'll basically converge to the value function. So after t iteration, what we have is for all the states, all s, vt of s, so at the tth iteration, minus v pi. So v pi is the true value function for the policy pi, is less than or equal to gamma to the t, v0 minus v pi infinity norm. Okay. So can someone remind us what is infinity norm quickly? So it's basically the maximal difference in the elements of the vector v, basically. Okay. So what we are seeing here is that if you do this process repeatedly, what you'll get is that the value function estimate that you have, vt, is less than or equal to v0 minus v pi infinite norm. Okay. So you start with some random v0 and you keep doing this and you eventually get closer and closer to the true value function v pi. Okay. So let's look at a demo for this as well to make this a bit clearer. So this is from Andrei Karpathy. It's called the DP world, right? So what you have here is a grid world that we're trying to do now is we're trying to find what is the evaluation of this policy. So right now what we're seeing is these arrows here show the policy currently. So right now we are basically being random at all these cells. We are being random between two actions here, random between two actions here, and so on and so forth, right? At this cell we are basically taking possibly 3 different actions. So the question is, what is the value function for this policy and how does this work? So if we do evaluation one sweep, what do you expect to see, by the way? So when I click this policy evaluation one sweep, under the hood is going to do policy evaluation that we just saw. Do it for one iteration only. So what do you expect to see? So what you might expect to see is that this reward gets propagated one step, right? So let's see. Yeah, so you have green here and reds here. Do it one more step. You're seeing reds around here as well. So red means negative and green means positive. And we keep doing this, we keep repeating. And at some point you'll see that the values stop changing too much, right? At this point, they've almost converged, right? So for this policy that we have here on the grid, this is the corresponding value function, okay? So if you repeat this, there's no more change happening right now, okay? And we'll revisit this demo again one more time after the algorithm is completed, okay? All right, okay. Okay, we've seen this. So now we spoke about policy evaluation so far, but there were 2 steps in the algorithm, right? Policy improvement as well was 1 step. Let's talk about that next. So here's the policy improvement. Just to remind you, what we do is we construct a new policy, pi t plus 1, as the greedy policy. So you evaluate the policy, find q, and take an argmax over a of q pi t s comma a at all the states. Now there is a beautiful theorem that basically helps us do this. What does it say? It says that if you have 2 policies pi and pi prime, and for all s you have q pi s comma pi prime s is more than equal to v pi. Suppose this holds true. If this is true, then policy pi prime must be as good as or better than pi for all s. So this is called the policy improvement theorem. If you go back and take a look, you search for policy improvement theorem, it says that if you have 2 policies pi and pi prime which satisfy this requirement, the resulting value function you get is basically v pi prime is greater than equal to v pi s. What does this mean? It means that if I have this requirement met, my policy pi prime can be no worse than the policy pi. Now the question to you that I have is, if you do this recipe, if you do a greedy policy construction, are you satisfying this requirement here? It turns out that you are. So the greedy policy construction recipe has baked in this requirement being satisfied. So what it means is that if you do this, you're going to get no worse policies at each time step, okay? So every iteration you do, you are going to get no worse policies. That's a very big thing to say actually. So a bit more formally, what you have is monotonic improvement. So for all s comma a pairs, your q pi t plus 1, so the new policy you construct, is no worse than than pi t. So pi t plus 1 is no worse than pi t, i.e. the value you get by following policy pi t plus 1 is no less than the value you get by following policy pi t. Okay? This is called monotonic improvement. And there is one more thing, one more question you might ask is, okay, all good, you get improvement, but do you terminate? Will you converge? That's the question, right? So turns out that you will. So the convergence guarantee is that v star minus v pi t infinity norm is less than equal to gamma to the t v star minus v pi 0 infinity norm. What does this mean? It means that if I start from some policy pi 0 and the value I get for pi 0 is v star minus v pi far away from the optimal value. After t time steps of doing this process, I'm going to be gamma to the t less than equal to that initial difference. So my difference in the value and the optimal value is contracting over time, right? So gamma to the t is basically a very small number as t grows, correct? Okay, any questions at this point? Okay, so just to summarize a bit, what we've seen is that we took this journey through policy iteration, which has two steps: evaluation, improvement. We saw evaluation and we saw some convergence guarantees for that. We saw improvement, and using the policy improvement theorem, we saw that the construction of policies via greedy approaches can give us monotonic improvement. Further, this recipe actually converges to the optimal value function. Okay. So one question you might have is, okay, all good, you can find V star, but how do you find pi from that? So any thoughts on that? If you know optimal value, optimal V star, how do you find pi from that? Right? Yeah, you can do argmax over the Q star. Okay. And there is one more implication of this recipe. The implication is the follows: that this approach will terminate in finite time for finite MDPs. Why is that? Because for finite MDPs, meaning that the state action space is finite, you have a to the s possible policies. Right? Think about this. You have a grid world with s different states. You can take a actions at all the states. You have a to the s possible policies, and this says that at every point you're going to do no verse. You're going to improve monotonically. Therefore, if your search is over a finite space, you'll converge in finite time. Right? Okay. So just to wrap this up in an algorithm box kind of fashion, what we have is the following approach. You have a policy pi 0, you do evaluation E, find V pi 0, do improvement I to find pi 1. Evaluate, improve, and so on to eventually get pi star and V star. So in a bit more, let's say, algorithmic fashion, what you have is you start with some random initial value function in policy, except for that the V terminal should be equal to 0, right? If you're at the terminal state, then you can get no more reward at all, so it's 0. And then you do the following loop, evaluation loop, where we spoke about this already. We apply the Bellman equation repeatedly to find the evaluation of the policy pi. That's the evaluation step. And then you do improvement step here. So you take the current value function V, and do an argmax over that value function. So this is the greedy policy construction pi s, and then this whole thing repeats. Okay. So hopefully that's clear, and let's go back to the demo and see this in action. Okay. So here is where we were, right? We took some random policy, which is given by these arrows and these 4 directional arrows here. And we found that this is how it looks. This is the value function for this policy, right? So arrows are the policy, the colors and the numbers are the value function for this. And now we'll do policy improvement, right? So let's do policy update. So here's what we find. So as you see, the arrows have changed here. So for example, at this state, you should be going left, is what the policy is saying now. And then we repeat evaluation again. So let's evaluate. Okay. Here is what we get now, and then do an update again. So here is the new policy we get, right? And eventually, if you keep doing this, that's what's going to happen. So you get the optimal value function. So it's all green, more green now than it was previously. This is the optimal, this is the V star, and this is the corresponding pi star here. So all the arrows here are showing the optimal policy. Okay. So just to repeat this whole process, reset this. It's very fun to watch this, so I'm just playing it a few times. So here is what you get as the optimal policy. Okay. So any questions at this point? Okay. Cool. So let's return back to our story. Okay. So this is all well and good, but we have a problem, right? Always in life we have problems. What is the problem now? The problem is that we have been talking about grid worlds so far, right? But what do we actually care about? So what we care about is large scale MDPs. Okay, we don't just want to do grid worlds, especially in autonomous system. We want to do large scale MDPs. For example, you might have this is an old RoboCup video. So here is a robot dog that's trying to walk to the ball here. And this was basically optimized using the zero order methods, and it falls down at this point. This is way back, right? It's many years old now. But this MDP is not a grid world, right? This robot dog has a continuous action space. It can apply torques on its joints. The state space also is continuous. It's got a LiDAR or a camera maybe on it, right? So our policy iteration approaches are not going to cut it for these problems. So more examples. We already saw the cart pole example, so no need to repeat that. Sorry. So here is an example of robot trying to learn to walk. So it's basically learning to walk in a very funny way, but it turns out it's doing better and better steadily. And again, this is not a grid world anymore. Why? Because the robot now has 17 different joints that it can control via continuous torques. So your search space now is a search over continuous action spaces. Further, your state space is now also continuous. So here it's learn to walk finally. And the funny thing is that it looks funny, but I have a 2-year-old son and he also walks a bit like this. So when children learn, they try to learn somewhat like this, when they try to learn to walk. Then here is another video from RoboCup more recently. So these are basically humanoid robots. They have learned to walk, and essentially in these robot soccer games, whoever walks better basically wins, essentially, right? So these are often trained using policy search-based approaches, which we'll see subsequently. Okay. And here is another video. This is basically a video game where you're trying to do search in RGB space, and the goal is to navigate this maze just via RGB images. So again, the state space, as you can see, is humongous, right? It's an RGB space, and the actions are also continuous. You're basically moving in this continuous world. Okay. So what we'll see next is something called approximate policy iteration. This is kind of the foundation stone for many recent policy search methods. And we'll see how it builds up on policy iteration and tries to introduce some deep learning components into it. Okay. So the key question is, the setting is as follows, of course. The state space could now be an RGB image, not a grid world anymore. You will process this via some deep net, maybe a convnet, to try and understand it. And then the hope is that this convnet will eventually give you the game action to take. So given this state, where should I go next? That's the key question. So more mathematically, how to approximately learn pi star using function approximation for large scale MDPs. And the key point is, like I said many times before, enumeration over state action pairs is not feasible at all. So now you can't maintain tables of QSA or VS anymore, because the tables are infinite, possibly infinite, or very large. Okay. So let's go forward on this. So the setting is as follows. We are considering large scale unknown MDPs here. So let's start with some restricted function class Q, and I'll tell you why in a bit. So let's say Q is the space of all possible functions mapping from S cross A to 0, 1 by 1 minus gamma. Okay. So the assumption here is that the reward you get is bounded by 1. So therefore the cumulative reward you get is 1 by 1 minus gamma in the infinite sequence setting. Okay. Right. So suppose that your Q is a collection over such functions Q. And why do we need this, right? The point is that you have to make some approximations here. You have to assume some kind of form for the value functions. So this Q could be possibly, let's say, all 5-layer regression trees, right? You have multi-layer perceptrons with 5 different layers and regression trees, or all 3-layer neural networks, all possible linear functions, and so on and so forth. So what I'm doing is I'm imposing some inductive bias here. I'm trying to say, I know that this Q function should be a neural network or a linear function or a decision tree, and so on and so forth. So I'm bounding my search space already by doing this. And then the game starts from this point. So what happens is that we can now, and one more restriction is that we can only reset according to S0 sample from U0. So it's a restriction, meaning that in this game that you're playing, let's say you're playing this first person navigation game, if the agent dies or the episode terminates, you can only go back to a certain starting state. And this is required to basically constrain the search space a bit. You're not trying to find what to do from all possible starts, but only from certain possible starting states. So to come back to my example, I'm going to try and find what I need to do from this dias point only to exit the room, not from all other points, okay? This helps me make the problem a bit more tractable. Okay. So again, like policy, the recipe is already fixed for us. It's policy iteration with some modification now. The modification is approximation. So like policy iteration, we have two different steps. The first is policy evaluation, and now you'll see a Q hat appearing here. So Q hat T is approximating Q pi T. Okay? So think of Q hat as an estimator for Q pi T. And then policy improvement is exactly the same. You take your estimated Q function and take an argmax over it to get the new policy pi T plus 1 S. Okay? Now the key point here becomes that how do you find Q hat T? How do you approximate Q pi T? And there what we do is we use supervised learning. We use regression to estimate Q pi T. So next we'll talk a bit about regression and how it influences or enters our discussion of policy search. Okay? Okay. So there are a few things here to first say. So this is the recipe we have. And by doing this approximation, we basically make some sacrifices. The first sacrifice we make is that there is no more monotonic improvement. So just to repeat or recall, that in policy iteration we had this wonderful result, right? That every new policy you construct is going to be no worse than the previous one. It turns out that in the approximate setting we can't guarantee that anymore. Now why is that? So any thoughts as to why that is the case? Why can we no longer guarantee monotonic improvement in approximate settings? So what you might be thinking is on the following lines, what you might be thinking is, what you have is in supervised learning regression, let's say, we are doing a quick detour, right, to establish this point. So suppose we have data distribution D and we sample the inputs from D and the outputs are f star x plus epsilon I, right? You have seen this already, I'm sure, but just bear with me for a while. So again, we have some distribution D from which we sample the input. The output is constructed using some ground truth function f star which you don't know, corrected by some noise epsilon I, right? So and the noise is zero mean and it's bounded by some constant C. Okay? So and the goal is to try and approximate f star using finite training samples. So I get these xi yi pairs and I'm trying to find what is f star, what is the underlying function, right? So how do we do this usually? So we basically introduce some function class f, right? Let's say f is the class of all functions, let's say 2-layer MLPs, for example, or 5-layer decision trees, for example. And then we solve the following minimizing problem, right? So f hat, our estimator f, is the argmin over this function space, f fxi minus yi whole square, right? Mean squared error, right? Minimum mean squared error. So least squares basically. And then there is a key thing that we need to note. The key point is that assume that f star belongs to f. This is called realizability. That the true function f star actually is a 2-layer neural network, let's say. Right? I mean, there could be a case where the true function f star is basically a decision tree and you're trying to approximate it using linear functions. Right? So then you're already lost. You can't do anything there. But supposing that you're in the right search space, you're in the right decision tree space, let's say, then we can expect the following wonderful result. The result is that the expected value of f hat x minus f star x whole squared over the distribution D is less than or equal to delta. Right? So there is a bound in how bad we can be. So whatever f hat we find will not be worse than this delta. Okay? And how does the delta grow with samples? Anyone knows? Anyone remembers? Right, so basically what you have is, if you have n different samples, delta will grow as root 1 over n. Okay? So that's why if you increase data, if you give more samples, your machine learning becomes stronger, it does better because of this result, right? But there is a key point here. What is the key point? The point is this D. So the moment you go out of distribution, right? The moment you have some D prime not equal to D, and you're trying to sample inputs x from that D prime, then all bets are off. You can be arbitrarily bad. So the point here is that machine learning is not black magic, right? If you have a distribution shift, a distribution mismatch, then you're done for. There is not much you can do. Now, why is this important for reinforcement learning? Why am I bringing this up for this context? Because in RL, remember, the data you get is used to train the next policy that you learn. So if you start with a bad policy, you get bad data, you get a worse policy, and this spirals out of control. So in the policy iteration case, you were happy because you were in the tabular setting, right? You could have these guarantees. But in the deep RL or large scale MDP case, the guarantees are off because you might learn on D, but then try and deploy the policy on samples from D prime. And then you can be arbitrarily bad. Okay? So next we'll think about how do we actually try and fix this issue in the approximate policy iteration approach. Okay. Yeah, so just to recap or repeat, deeper nets or more data do not help with this distribution shift. That's the key takeaway from this point. So to come back then, I mean, I'm going to just give you the result now. I'm not going to go deep into this because it's a bit more involved. But there is a very nice lemma that we have. It's called the performance difference lemma. So it characterizes how different policies are and how can we bound their value function differences. So just to repeat, the recipe we have is evaluation approximately, an improvement on the basis of that approximate Q function. The PDL, performance difference lemma, says that what you can say is V pi t plus 1 S naught minus V pi t S naught is basically this quantity here. Looks a bit involved, so let's parse it out. So what we have is that I'm trying to talk about, I'm constructing pi t plus 1 in a greedy way from pi t, and I'm talking about what is the value function difference in these two settings. And it turns out that I can say that this difference is basically 1 over 1 minus gamma, expectation over states, expectation over actions of the advantage function. What is this? Advantage function is basically just Q minus V. So Q pi t SA minus V pi t S is the advantage function. So what it says intuitively is that if you have a certain average value you might get, how much better is the action A going to be as compared to the average you might get in that state. Right? So for a certain state S, I can get value Vs on average. But if I take action A, I can get Qs comma A. So I'm going to subtract those two things. So Qst minus V is A pi st, A pi t sa. And it turns out that V pi t S naught minus V pi is equal to this value here. Okay? So this gives us a way to characterize how far away or how bad I am being if I take a policy update step. Right? So what we have is a recipe now. The recipe is, of course, without any derivation. I'm just giving the result directly to you. Is that we can make a mixture policy. So retain your pi t and take some portion of pi prime. So let's say you have pi t, you take pi t, construct pi prime greedily, and the new policy pi t plus 1 becomes a combination, a mixture over two distributions. So you have pi t and pi prime, and you have 1 minus alpha plus alpha here. Okay, so it's a bit involved. I know it's a bit unsatisfactory for you guys because I'm not deriving the whole thing here. I'm just giving the result directly to you. But the idea is that you can take an old policy and just take a small step to find a new policy and merge the two, mix the two in a certain way. Okay, and if you're interested, this is called the conservative policy iteration approach, CPI. And have you heard of PPO and TRPO and those methods? You may have, right? So those are all fundamentally built on this approach, right? So take a step, but don't step too far, and take mixture policies. Okay. Okay. So let's move on. So any questions at this point? Okay. Cool. So again, this is the end of this section, approximate policy iteration. And again, as always, we have a problem. So what is the problem now? So what is bad about this approach, let's say?
Generalization across distributions.
Who said that? Sorry. Yeah. Okay.
Generalization across distributions.
Okay. Why is that?
We're not able to, learning one regression distribution does not work out of sample.
Yeah, absolutely. So what you might do is you might still hit the same generalization problem, right? You might still hit the distribution shift, distribution mismatch issues. So what you can do next, what we'll talk about next quickly, is something called policy gradient approaches and autocritic methods, right? So the idea here is that in the CPI method, we basically said, let me take a policy and step it forward a bit and mix them two. But instead of doing, okay, let me go back. So the key point here is that being greedy here, right? You take some Q value and you construct a policy that's being completely greedy with respect to that. That is the key point here, which is being used. Now, being greedy means that you're taking a step completely in the max direction, right? But what is the problem there? The problem is that the Q function estimate will be completely off, right? So if you have a wrong estimate, what is the point of taking a complete max step on that wrong estimate? So what we'll see next is, can you take a smaller step in the direction but not completely commit to it, which is where the gradient comes into the picture. Okay. So to do this, we have to build up a few concepts first. Let's build up something called sampling. Okay. So I'll remind you again. This was the objective function we started from. So now we can write this objective function as r tau. So let's denote this part as r tau, right? R tau is sigma t equal to 1 to t, r stat. The objective now becomes j theta is expectation over p theta tau r tau, right? Hopefully you're with me so far, right? So I'm writing this out in a parametric way using r tau. So how would I find this? Suppose I give you a policy pi and I want to try and find what j theta is. How would you find this? How you would find this is basically written down here. What you'll do is you'll try and sample multiple times from the distribution. And you get these examples of R, SIT, AIT tuples. You get these trajectories. You capture them all together and you average over this entire set, right? So you're trying to find an expectation at the end of the day, and you can do this using sampling and averaging, correct? So this is basically a backdrop to try and set up the policy gradient approaches, okay? So just to recap, this was a way to try and compute the objective function j theta using sampling based approaches. So because of lack of time, I won't go very deep into this. I'm just going to give you a quick run through and then cover other things as well. So the idea here is that you can basically write the gradient of the objective grad j theta as this, right? Integral over grad p theta tau r tau d tau. And then you can use something called a score function trick, which basically says I can write this only in terms of my grad log probabilities. Okay, again, no derivations here, but just the name is the score function trick. Okay, so what you get by doing this eventually is, this is the grad log p, and one key point here is that this does not depend on the transition dynamics or the initial state distribution. As you can see here, the grad log p is basically only a function of the policy pi theta. And why is this good? It's good because think back to your RoboCup soccer examples. There is no one who's going to sit down and give you a transition function p, right? So you have to basically do things in a model-free way. And therefore, this expression here is a model-free expression. It does not need transition dynamics or initial state distribution, okay? Okay, so here is an example to just concretize this a bit more. Suppose we have a very simple MDP, right? A single state, single action MDP. And I'm just going to work through what is the resulting expression for the gradient in this case. So what we have is we have a stochastic policy, suppose pi theta, which samples according to Gaussian distribution n, parameter by theta 1, theta 2, okay? So what you have is log pi theta, right? We saw this expression here. This is what we care about. It's called a score function. So anyone seen score function in other contexts? Yeah, right? Diffusion models use score functions, right? So they also appear in the policy gradient approaches. So what you have here is basically log pi theta a given s is basically from this Gaussian expression you can find that this is this expression here. And the grad of that turns out to be this expression here, right? So grad with respect to theta 1 is this a by theta 1 by theta 2 squared. And for theta 2 is this expression here. And suppose you have these different examples here. You have three different experience tuples. So you set the parameter theta to be 0, 1, and you take actions 0.5, -1, and 0.7, let's say, for example. And you get these three rewards, RSA equal to A in this case. So to compute my gradient, I'll basically take those three examples and average them together. So my grad theta becomes 0.58 and -0.244. The numbers aren't important, it's just to give you the idea as to how this whole thing works. Okay? So now once you find the gradient for a policy, what do? What is the natural next step to do? Right, so just to recap, just to sort of set it up again. You have the objective function j theta, you have the gradient. What do you do next to optimize the objective function? Right, absolutely. So what you do next is something called gradient ascent or descent. In this case, it's ascent. You're trying to maximize the objective function. So you have this basic idea called reinforce. This is like the canonical policy gradient approach. How it works is it basically says I'm going to compute the gradient by sampling. So it's going to compute the score function and keep a track of the running rewards it gets and take an average over this quantity, right? So basically run your policy in the environment, run your robot multiple times, gather experience, store the rewards, store the score functions, take a product of those two and take an average over all these samples. Okay? So how does this whole reinforce approach work? You start with some differentiable policy parameterization, let's say pi as parameterized by theta. You're trying to find what should theta be optimally, right? So the step size alpha is more than 0, let's say, and you start with some initialization. And then here is the loop. You basically generate episodes, right? So drop your agent in the world, get episodes, get experience, compute the return by doing this, and take a gradient ascent step. So theta plus alpha is the step size, discount factor, and this grad log prob term appears here. So this went by a bit quickly, but the idea is to give you a basic idea as to what this approach is doing, right? You can go back and take a look at the details on your own time. Okay, so for the sake of time, we'll skip the notebook bit for here and we'll carry on forward. But there's a notebook which influences, and the idea is very simple, right? You take your neural network policy, in PyTorch, you then basically compute the gradient by doing backprop on a pseudo loss function, and then you have this approach that you can follow. Very simple idea. Okay. And then it turns out that this approach has some variance issues. So people have come up with something called actor-critic methods. So if you hear the term actor-critic, it's basically policy gradients, but with some tweaks to make the variance reduction in the gradient estimator. Okay. So visually, how does it look? It looks as follows. You have two things now. You have actor. The actor is the policy pi. The critic is the value function estimator. Let's say it computes the Q value. So in the first step, you have the actor taking an action AT. In step 2, the critic gives you the Q function of that SA pair. Okay. So think of it like a DQN agent possibly, saying what is the Q value for my current SA pair. Then the action is stepped forward. The environment returns back with some new reward and state. So this is your basically experience gathering step going on here. And then here is the change in the policy. So grad theta, or delta theta, sorry, is this alpha grad log prob Q, which we already saw in the previous slide. So it's a different instantiation of the same idea, right? So earlier in the previous slide, we had the raw returns here, but it turns out that if you use value function, you have the lower variance in the whole process. And finally, you have the step 5 where you're trying to change the critic parameters as well, right? So both the policy and the critic are being updated simultaneously. So you can think of it like the policy and the critic are both learning together and learning to be better simultaneously. Again, this was quite high level. You can go back and take a look at actor-critic methods for more details in this idea. Okay, and how does this perform? Just one quick performance evaluation slide. This is back from 2016. So these were all the Atari games, basically 5 Atari games where DQN was state of the art at that time. And what they find is that actor-critic methods could actually do much better than DQN, as the yellow line shows here, getting much higher reward, much faster as well. And one more key point here is that DQN took, at that time, 8 days on GPU, whereas actor-critic can take 4 days on CPU. It was also much faster. So why is it much faster? Why does this make sense intuitively in this problem specifically? Any thoughts? So it's faster because if you think back to the breakout example that we showed a video, right? The paddle has to move left, right, and hit the wall. In the value function or DQN based way, you have to reason about the value function completely. Whereas in policy search, you're trying to search in the policy space directly. So it's a much smaller search space. Hence, it's much faster in the learning. Okay? Only for that example. It's not a broad statement. I'm just saying in one example. Okay? So an open question now also is that which method should you go for? Should you go for value based or policy based? And the jury is still out as to this question. Okay? All right. So now I'm going to shift gears a bit. This was basically, we covered some ideas on policy search. We covered zero order methods, so Hooke, Jeeves, cross entropy. We covered policy iteration, which was basically 2-step evaluation improvement. We showed some guarantees in that approach, i.e. monotone improvement and convergence. We spoke about approximate policy iteration and policy gradient approaches. And now we're going to shift gears into some research frontiers, right? What are people working on currently based on these foundations, okay? So here is one example, right? So imitation learning is one example. So why does this matter? So think about this. The key point here is that when rewards are not known, so in the previous session also we saw this point being made, that reward shaping is a very important thing. If your reward function is bad, then your learning is going to be bad for sure. One more thing is that when we as humans learn, right, there are not reward functions given to us all the time, right? So often we learn by looking at other people, right? So I might be looking at how you run and learning to run myself. So the research frontier here is that using these foundations, let's say policy gradient, policy iteration, etc., but having no reward functions whatsoever, how can we still do learning, right? And here is a motivational video for it. So here is a baby, and it's the baby is being shown certain actions. And promptly the baby basically copies that action. So imitation is something that is foundational to the learning process in us as agents, right? And here's another video where this process was followed for robot learning. Yeah, this is very, very interesting, but we have to still carry on. So this other video here is you're showing this robot arm how to do this ball in a cup catching task. So there is a ball on a string, you're trying to catch it. And it's very hard to do this by programming in reward. What is the reward function to give, right? Very hard to give. So it's learning by imitation learning in this case. It saw the demonstration and it's going to just learn by doing that. So the question to you is, why is the reward hard to specify in this problem? Any thoughts? So the challenge here is that you have to give some reward at every possible state action pair, right? How do you write that function mathematically? How do you even say what it is? Of course, you can say the reward is 1 or 0 if the ball goes into the cup finally, but in the interim points, RSA, what is that? It's very hard to say mathematically, right? So here is an example of imitation learning in action. So again, this is going to be not very technical, it's going to be more examples and videos. So this is the Alvin system, which was basically using imitation learning to drive a vehicle, this vehicle specifically, by mapping state action pair directly, right? So the vehicle has to, it has some camera on top and it's trying to navigate this road. And it's learned by observing how a driver drives in this vehicle. So it's autonomous driving completely and learned using imitation from drivers driving. And more recently, this is another video from NVIDIA where you have a vehicle that's trained using imitation learning. This is the NVIDIA vehicle. And it's not doing very well. As you can see here, it goes and hits cones and throws them out. But turns out that if you can provide more data and do better techniques of imitation, you can get it to drive very well. So subsequently, you'll see that it's doing much better now. Yeah, so after a while, it basically learns to do better. After 3,000 miles of learning, you can see much better driving performance. So here it navigates the road quite well. So again, the key point, the takeaway message here is that even without rewards, just by observing what humans might be doing, you can learn using RL principles called imitation learning. Okay, so we can skip this, more examples. And so this is examples on race car and Mario, trained using imitation learning again. You can check out the sources subsequently. But there is one more idea here. The idea is that why do we want to throw away reward functions, right? When we learn, we often learn not just by watching you, but by understanding what you want. So what does that mean? Let me show a video for that. Okay, let's skip this. So this video is very interesting. So here the researcher is trying to perform an action. He's trying to put this plate in the cupboard, and the agent is observing him. And at some point, you will see that the child goes in to help the person. And this is beautiful. It's interesting because we humans have an understanding of the underlying reward function of this person here, right? So the point is that if we can recover the reward function, we can use that information to do better learning, right? So reward functions have a lot of information. Let's not throw them away. Let's try and recover them somehow and do better learning based on that. So how much time do I have, by the way? 5. Okay, cool. Okay, so I'll quickly just summarize some of our recent work on this area. So I'll take you back to one of the initial slides that we saw. So the goal was to try and model how humans drive by looking at data from various sources. It didn't look well at that point, right? All the vehicles were crashing. I'll just remind you again. So you have bad things happening essentially, right? So what we said is let's not try and do supervised learning. Let's try and do imitation learning, and specifically inverse RL on this problem. So I'll talk a bit about how we approach this problem from that standpoint. So firstly, we tried a model-based approach. So what does this mean? What it means is that suppose you have an underlying model of how humans drive. So you first characterize what is the spacing between different vehicles. Let's say, as a human, I want to maintain a certain spacing between myself and the vehicle in front. And it's parameterized by some parameters, let's say A max, B pref, D min, and so on. So these parameters basically say, am I aggressive or am I a passive driver, right? Aggressive people will have very high A maxes. I want to accelerate a lot. And then based on that on the spacing I want, I can calculate the acceleration I want to take. So A IDM is A intelligent driver model. So I can get this A based on the A max parameter from this desired velocity. So desired spacing, etc. Right? So I have this underlying model. The model is not very important. We have some model, let's say, from driver modeling literature. And the goal is to try and find what these parameters are using various approaches. Okay? So what we did is we cast this as a Bayesian inference problem. So suppose we have theta as the parameter. So these theta is this A max, B pref, and so on. And we have a sequence of positions of the vehicles. We have yt plus 1, yt, and yt plus 1, and so on. The goal is to try and find distribution P over the parameters theta, having observed the sequence of positions of these vehicles. That's the model-based approach. Okay? I hope the goal is clear. So just to recap, the goal is that I'm observing these vehicle positions and trying to find the parameters of the underlying drivers based on those positions. So how do we find this? What we can do is we can do recursive Bayesian estimation to try and find this distribution. So the eventual parameter setting theta capital T can be built based on t minus 1 recursively. Okay? So what methods might you use for solving this approach? Any thoughts? So it's basically Bayesian inference problem. So what we tried was particle filtering. So how does it work? We basically maintain a belief over particles and we evolve them over time, right? We try and solve this recursively using particle filtering, right? So no details, but just the idea is that you have this bucket of particles and you try and reweight them according to what you saw in the ground truth data. Okay? And this is an example of how it works on a real world simulation environment. So in this video, you'll see a white and a blue color. So the white is the ground truth demonstration and the blue is our model performing that imitation on that same demonstration. So here is how it looks. So white and blue are overlapping, which means a good thing that our approach is able to capture what the underlying parameters are of these models. Okay? So here you can see that the vehicles are overlapping quite to a nice extent. But there is a problem here, as always. The problem is that the whole approach here relies on underlying models being available. But we said that we don't want models to be always necessary, right? We want to do model-free learning as well. So the next thing we tried was imitation learning based on GANs. So the idea is that we can recast this problem. So the idea is, suppose there is some true cost function, right? C true, which we don't know. There is no reward function or cost function known to us. But suppose it's called C true. The goal is that my learning agent pi incurs less or equal expected cost than the expert pi e. So pi is the expert policy, so human-driven policy. I'm trying to learn a policy pi myself. And we can recast this as a minimax problem that looks very much like GAN problem. Okay? So this is generative adversarial imitation learning. We basically have the policy being the generator and the critic being the discriminator. And we play this two-player game between the policy and the discriminator. So here is what it looks now. So all the blue vehicles are driven by our Gale-trained policies. And we find that there is no longer any bad things happening as it was happening earlier. And interestingly, one more thing is that the distribution we get over the speed, let's say, The black is the ground truth human distribution of speeds, and the green is our method as compared to an orange baseline. So our method also seems to match the distribution to a great extent over the speed. Of course, the caveat is that this is a cherry-picked video. It's not always this good, right? So this is, of course, not good all the time, like all deep learning approaches. Okay, so I think with that, I will stop here with the technical part. I'll just quickly go to my slide mode and conclude. So bear with me. Okay. I think I have only 2 minutes left.
Yeah, but maybe we start a bit late, so yeah, you can take a few extra minutes.
Okay, cool. All right. Okay, so then I'll cover a bit more stuff. Thanks for bearing with me. Okay. Okay, so we just saw this. So this concludes the imitation learning part of things, and I want to next talk about a few more recent things we are pursuing in our group. So this is work led by my student Mahesh Keswani on safety representations. So we're thinking now a lot about safe reinforcement learning. So what does that mean? I'll just quickly introduce that and then we can wrap up. So RL basically is this, right? We have this Atari breakout problem, or we might have this emergence of locomotion or learning to walk, for example. But safe RL is a different thing. The safe RL means that what if you have constraints now? So you're trying to have this agent go to different locations here, but while avoiding crashing into different obstacles in the way. So one example could be you're having this agent trying to learn to walk, but it has to always be within a certain velocity. It can't exceed certain velocity limits. So the red circle here shows when the agent is going beyond a certain velocity limit. Okay. So now the question becomes, okay, how do we do RL or learning under these constraints? That's called safe RL. So the setting is as follows. We have the same, on the left we have the usual RL. On the right we have safe RL, right? So there are a few new constructs in this thing. So what we have now is we have the SATR as usual. What we also have now is a cost function C and a cost limit beta, right? So the agent takes a certain action, it gets the usual reward and the usual next state, but also gets a cost function from the environment. And now the problem setup is a bit different. It's basically you're trying to find pi star, which is argmax over the space of policies, but the policy space is actually a feasible policy space now. What does that mean? That the policy has to adhere to a constraint limit. So JC pi has to be less than or equal to beta. Okay? So I'm trying to find all those policies JC pi, and then within that feasible set, I'm trying to find what is the optimal pi star. That is the safe RL problem. Okay? So what we found is in this case that the information about safety matters a lot. So imagine this problem. You have these different water worlds. So the agent is shown in green, in blue. It has to get to a goal G and avoid the water in dark blue, right? So the agent gets a reward for going to the goal and it gets a cost for hitting the water states, okay? And what was found is very interesting, that if you have vanilla DQN, it's shown in the green here, versus if you provide DQN with some information about ground truth safety. So how far away is the agent from the water cells, then it gets much higher reward. And the reason is very clear. The reason is because if you have the Q values plotted here, if you have no ground truth safety information, all the Q values, as you can see, are bunched together, right? Whereas if you have safety information, if you have, let's say, you're 1 step away from the water cell, 2 steps, 3 steps, etc., the Q values are nicely segregated into different clusters based on the safety information. So we basically use this idea in autonomous driving, and I'm going to skip all this and just show you the results quickly. So I'll just show maybe one video. Okay. Right. So this is on. This is on the Waymo open motion dataset. It's a real-world dataset from Waymo on autonomous driving, and we basically used an underlying canonical baseline safe RL algorithm, TRPO-PID, and that's how it looks. Oh, sorry. Wonder if I can play this. Yeah. So the vehicle basically goes here and crashes, almost comes to a crash using this approach. And our approach using safety representations comes to a more graceful stop here and then goes further. So the point being that if you can put safety information in the learning process, you get better behavior in the real world settings especially. Okay, so with that I'm going to just start concluding. Let's see. Okay. Okay. So in conclusion, what we basically what we are working on in the group right now is two directions. One is using safe RL methods and using VLMs, vision language models, for safety guidance. Because often just providing these constraints is very, very hard. So can we leverage vision language models for some inherent common sense knowledge about safety and leverage that into the RL process to try and learn safe policies? So what did we cover in this session, right? Just a quick summarization or recap for your benefit. So we spoke about how to contextualize RL in the AI landscape. We spoke about example MDPs and how to think about policies. We spoke about policies a lot. We then talked about various methods of searching over policy spaces. We spoke about how can we bring in approximation and deep RL into the picture, and then how do we sacrifice guarantees in that context. And then we spoke about a few research frontier directions like imitation learning, inverse RL, and safe RL. So with that, I'll just conclude saying that it's exciting times for us because now there's a lot more agents in the real world working now. So this picture is becoming more relevant day by day. And I am working on these different themes here. So robots, control systems, human AI interaction, RL planning, with such characteristics like real world interaction and real time operation. So with that, I'll stop here. Thanks for your attention. Very grateful for the opportunity again. Thank you. Okay, I can take a few questions.
So thank you for the wonderful presentation. So you presented two methods to find transition states. So one using transition probabilities and another using approximation theory, which relies on trained data. But approximation sometimes can lead to biased outcomes. So is there any method to incorporate both techniques which could provide better results? Thank you.
Okay, so I'll repeat the question to make sure I understand it. The question was that we spoke about a method that basically uses transition dynamics, uses the knowledge of the model. There was one side. The second side was, can we use approximation directly? But approximations can give you biased outputs. You sacrifice something, right? So is there a way to try and blend both, the best of both the worlds? That's the question, right? Okay, so very interesting question. So the point is, approximations do make you sacrifice things, but they also give you tremendous power. So like we spoke in the session as well, large scale MDPs, you can't tackle them with model based approaches. So you have to go approximation route, and there this conservative PI and TRPO, PPO, etc. have very solid foundations on optimization theory, which says that can you stay in the neighborhood where you don't make the sacrifices anymore. So therefore, the approximation based methods also are aware of the sacrifices they make and are accordingly trying to make the methods more robust. That's one. The second point is there is a very interesting line of work on model based RL. What it says is that I'm going to try and learn models from data and then do model based planning on those models. Now there very interesting work is happening in trying to, let's say, learn diffusion models over the data that you have seen. So if I'm doing, let's say, learning to walk, I have all this data and then I try and learn diffusion model which tries to give me the transition probability in that walking problem. And then once I have the transition probability, I can then just do model based planning and my guarantees are back. So two answers. One is that you can either do model based planning, which is of course quite difficult to do, but very active area of research. The second is the methods that are being developed are already cognizant of sacrifices and they're trying to deal with that in the formulation itself. Thanks.
Thank you, sir, for the wonderful lecture. And my question is, how in maybe like a transformer architecture or auto-regressive architectures, we are for better learning we do teacher forcing. Why are we not able to directly use RL and not directly borrow methods of say LLMs into RL?
Okay, so the question is, what can RL learn from LLMs, and what methods can we bring into the RL space, right? Absolutely. So you can take a look at something called decision transformer, which basically says that I'm going to take this whole problem and cast it as a transformer problem. How? I'm going to try and map my state action pairs to a predicted return. So then it becomes a sequence to sequence problem basically. So you have a sequence of state action pairs, you have a sequence of returns, and the transformer is trying to just model this process. And then all your machinery of transformers enters the RL picture directly. So take a look at that paper called Decision Transformer.
Sir, thank you for the wonderful lecture. I was just asking in the approximate policy accuracy that was just mentioned in the slide. I raised a question of what are the formal statistical bounds that I mean on policy performance when the visitation frequency, I mean deviates from the data distribution mean. That you mentioned the last approximate policy accuracy.
Yeah, so your question is, in the approximate policy iteration, what are the statistical evaluations or bounds that we can get on the state action visitation frequency, on the policy performance? Yeah, so there are results on this, and I'll refer you to a nice textbook by Alek Agarwal, Sham Kakade, and Wen Sun, and there's Nan Jiang. It's called RL Theory. It's a very recent, ongoing, in the process work. Take a look at that book, and there you'll find some statistical bounds on distribution shift problem. Yeah, yeah.
I just asked more questions and discussing later.
Sure, absolutely. Thank you.